Hi there, let's move on our classical mechanics course and solve one exercise that involves integration of Newton's second law. Consider the following. There's a rope part lying horizontally and part hanging vertically. Because of the weight of the hanging part, the whole rope is going to fall. Assume there's no friction. We want to study this falling behavior. What is the amount of rope hanging as a function of time? Also, what is the velocity of the rope when all of it loses contact with the horizontal surface and all of it falls down? To answer this, we need to write Newton's second law. But now, considering that only the portion of rope hanging is the one contributing to the weight that pulls the whole rope down, but the whole mass of the rope has inertia. So I need to write the force of gravity as a function of the amount of rope that is hanging. I'll write the mass as a function of the density of the rope, rho, and we'll assume that the density is constant all through the rope. The total length of the rope is L, and the length of the rope hanging down is Y. The total mass is then rho L, and the mass hanging is rho Y. The total force pulling down is then rho gy equal to rho ly, two dots. Rho cancels and I solve for y, two dots. This is the differential equation we want to solve now, which seems easy, doesn't it? The only function whose second derivative is proportional to itself, being positive, the constant of proportionality, is the exponential. So the general solution for y is y of t is a times e to the power of alpha t plus b times e to the power of minus alpha t, where alpha is the square root of g over L, and a and b are integration constants. Double check that this is correct. If the rope is initially at rest, we can substitute this in the equation and find a and b. Y dot of 0 is 0 and y of 0 is y naught. We get that y of t is y naught over 2 times e to the alpha t plus e to the minus alpha t. But this is the hyperbolic cosine of alpha t. This is the equation of motion of the tip of the rope or the length of the rope hanging, from where we derive and get the velocity. Y dot of t is equals to alpha y naught hyperbolic sine of alpha t. Now, for the velocity of the rope, right at the moment when all of it is falling down, we're interested in the time when y is equal to L. For that time, capital T, the length, is equal to L. Let me use now some trigonometric identity. The hyperbolic cosine square minus the hyperbolic sine square is equal to 1. From this, I substitute the hyperbolic sine by the square root of, and from the equation of y of t, the hyperbolic cosine of alpha t is L divided by y naught. So I end up having that the velocity at time capital T is square root of GL times square root of 1 minus the initial ratio of the rope hanging versus the total length of the rope.
I could give you my word as a Spaniard.
No good. I've known too many Spaniards.